State the principle on which an AC dynamo works. AC dynamo is nothing but a current generating device, so it is going to generate electrical energy by consuming mechanical kinetic rotational energy. So whenever magnetic flux passing through a coil changes an EMF, is induced in it, with the result that the current flows in the coil. So when there is a change in magnetic flux, EMF changes, as a result current flows through the coil. It converts mechanical rotational kinetic energy into electrical energy. There are something what is known as carbon brushes. When we draw the figure of a AC generator, we saw that there is something what is known as a carbon brush. They are asking you what is the function of these carbon brushes. Carbon brushes are used to make contact with the commutator to supply current to the armature. So if these carbon brushes were not present, then we would see that there would be a break in current or break in contact. In order to have a perfect contact, we are using this in case of a DC motor as well as in case of a AC generator, wherein the generated current is passed on to the load. Next question, what is the magnitude of EMF that is induced in the coil when its plane becomes parallel to the magnetic field? The induced EMF is maximum when the plane of the coil is parallel to the magnetic field. Another simple question that they ask is, name the principle on which the functioning of a transformer depends. Well, the functioning of a transformer depends on the principle or the phenomena of mutual induction, wherein there is a change in magnetic flux in one part of the circuit. Automatically, because of the permeability, we see that there is going to be a corresponding change in magnetic flux as far as the second part of the coil is concerned. What is the function of a step-up transformer? A step-up transformer is nothing but it steps up the voltage across the secondary for a very small input of voltage. So to increase the voltage, we are using the step-up transformer. Let's consider this question that they have asked as far as induced EMF is concerned. They're again asking you the magnitude of induced EMF is dependent on which factors? State the factors on which magnitude of induced EMF depends. First one, the magnitude of induced EMF depends on the rate of change of magnetic flux. It is directly proportional to the rate of change of magnetic flux. Second one, it is directly proportional to the strength of the inducing magnet. That means the magnetic strength is definitely responsible for the induced EMF. Third one, it is directly proportional to the number of turns of the coil. Greater the number of turns of the coil, more is the magnitude of induced EMF. Fourth one, it is directly proportional to area of cross section of the coil. Greater the area of cross section of the coil, more is the induced EMF. Another interesting question here. Can a transformer be used on both the current sources? Can a transformer be used on both the current sources? That means can it be used on AC as well as DC source? And you're asked to justify your answer. Well, a transformer is used to change low alternating voltage to a high alternating voltage having the same frequency and vice versa. So it is only used to convert an alternating EMF from a lower value to a higher value. The transformer cannot be used with a direct current purely because you need a change in magnetic flux. The change in magnetic flux can only occur when it is an alternating source and not with the direct source. So here definitely we are going to use the concept of mutual induction to a transformer with respect to change in magnetic flux and not with the direct current. It is used with an alternating current source only because its working is based on the principle of electromagnetic induction, that is change in magnetic field due to varying electric current. Another one that they ask generally is, state the two characteristics of a primary coil, that is the input source, for a step-up transformer when compared to a secondary. So they are asking you the characteristics of a primary coil in case of a step-up transformer. In case of a step-up transformer, as I said, we are going to increase the voltage across the secondary. Since we are increasing the voltage across secondary, the number of turns of secondary is more than the turns of primary. That is, number of turns of primary less than the number of turns of secondary. I have to obtain a higher voltage across secondary. Since I have to obtain a higher voltage across secondary, I should have the wire having least resistance. With least resistance, I'll have more cross-sectional area, where resistance is inversely proportional to cross-sectional area. Greater the area of cross-section, less is the resistance. So I see that the primary wire is thinner than the secondary as far as a step-up transformer is concerned. Why do we transmit alternating current at high voltage? They are asking you, when we have these high tension wires that are taking the electricity from the mains to the, or from the hydroelectric power plant to the end consumer, why does it carry at a very high voltage? Electricity transmission is done at high voltage purely because, as at low current, the energy lost during the heating, the energy that is lost due to heating effect, which is given by the relation energy loss is equal to I squared RT, that is, I is the current, R is the resistance, and T is the time, will be reduced considerably. And when it is reduced considerably, further low current thin wires can be used, which proves it to be much more economical. So we can prove why we are using it at high voltage is purely because of the energy loss in terms of I squared RT and in terms of thinner wires to make it much more economical. Next question, what are the causes of energy losses in a transformer? When we studied transformer, we studied three types of losses. One was because of the resistance that the wires of primary and secondary coil would apply. Second was the eddy current loss, which causes the heating effect in the coil. Third was the hysteresis loss, that is the magnetic loss that has been incurred in it. This magnetic loss is purely on the basis of mutual induction, wherein the coil is setting up its magnetic field, allowed to permeate through the soft iron core material, thereby converting it into magnet, which has its own magnetic field. Next question is, how can you minimize these losses? See, after all, you are using a device so that you get less amount of losses, or more is the efficiency. How do we minimize it? The first method of minimizing the loss is that the losses due to resistance can be minimized by decreasing the resistance of the wire or by using thicker wires. So greater the cross section, less is the resistance. Second, the hysteresis loss can be minimized by using better quality of core material, where majority of dipoles are generally aligned linearly. So the moment I have linear alignment of dipoles, definitely the magnetic losses would be reduced. And eddy current losses can be minimized by using a laminated soft iron core material. The lamination can be done by insulating materials such as mica. Talking about board point of view, as I said, this chapter is more on a theoretical part rather than the numerical part. There are no numericals that are basically coming into this particular chapter. Though there are certain formulas that we have shown certain mathematical relations, but as far as boards are concerned, we definitely do not have numericals that are based on this chapter. This is entirely a theoretical and diagram based question. So you should pay attention more on the diagrams, on the figures that are to be drawn, more so over on electric bell, AC generator, DC motor, step-up transformer, step-down transformer. And of course, those laws and rules that we are governing while drawing the magnetic lines of forces across a straight conductor and circular loop. So this being a diagram-based question, definitely more weightage on it. Similarly, as I said, we should know the laws, not the statements, but the application to it. As to how is it that the force is experienced? How is it that the magnetic lines of forces are being generated? How is it that we are getting the direction of force that is being experienced on the conductor? So all the applications of laws come across as far as the various examples or devices are concerned. Let's consider this chapter as far as the boards were concerned. How or what are the types that appear in the boards for this particular chapter? This being more on the theoretical part, more on figure-based or diagram-based questions. Most of the times you see the appearance of questions that appeared were more on diagram-based rather than even description. So let's consider year-wise which are the questions that basically appeared in the boards from this chapter. First that appeared in 2002 was a diagram-based question. They're asking you to draw a neat label diagram for an electric bell. While drawing the electric bell, one should be very careful while naming the parts. You should name the gong, you should name the hammer, you should name the adjusting screw, you should name the electromagnet, you should also name the armature, and you should name the battery as well as the switch. So all these components are vital parts of the electric bell, which definitely you should show with proper connections and connectivity, indicating the flow of current through the circuit. So the diagram itself should explain the construction, the working of an electric bell. So when you show it with the help of the current flow diagram, definitely you know how the current flows through it, how the electromagnet gets magnetized, how it attracts the armature, which is carrying the hammer to strike the gong. This was asked for around 4 marks in 2002. A very important diagram to be studied for. Another question that was appeared in 2002 was, state 2 advantages of electromagnet over bar magnet. As I said, electromagnet, you can definitely increase or decrease the strength of the electromagnet by increasing the current or by adjusting the current. And second one is that it produces a stronger magnetic field as compared to a bar magnet. We can also change the polarity of an electromagnet as and how the need be, as compared to a bar magnet wherein the polarities are fixed. So these are the basic advantages of electromagnet over bar magnet. This had appeared for 2 marks in the 2002 paper. Another question that came in 2002 paper was, state 2 dissimilarities between DC motor and AC generator. 2 dissimilarities, that is differences. First one, a DC motor converts electrical energy into mechanical kinetic rotational energy. Electrical energy into mechanical kinetic rotational energy. Whereas an AC generator is the reverse process. The mechanical kinetic rotational energy is supplied and it's converting into electrical energy and hence called as a AC generator. Then coming down to 2003, we have a diagram that was shown on the paper wherein you have a coil that is wound across and is connected to a galvanometer. You are having the north pole of the magnet that is entering the coil and they are asking you to explain why deflection is occurring in the galvanometer. Second, does the direction of current in the coil appear clockwise or anti-clockwise when viewed from face A? So you are viewing from face A, you have to determine whether current direction is anti-clockwise or clockwise. Third subpart of the question is, state the observation in G when the coil is moved away from N. So you are moving the coil away from the bar magnet. You are asked to find out the deflection in galvanometer. And fourth part is, state the observation when both the coil and magnet are moved towards the right at the same speed. So you are moving both the coil as well as the magnet together with the same speed. You are asked to give the observation. This had appeared for 5 marks in the boards. Well, the first one, explain why deflection occurs in the galvanometer. As I said, deflection occurs in the galvanometer purely because magnetic lines of flux are made to pass through a coil, and when magnetic lines of force are made to pass through a coil, we see that the current is generated in the coil, which is shown by the deflection in the galvanometer. Galvanometer is a current sensing device. The moment we see the deflection, we can automatically say that the current is flowing in the coil. Second part of it, does the current direction appear clockwise or anti-clockwise? Now here we see that the north pole of the magnet is moving through the coil. So when north pole moves towards the coil, the end of the coil would have a south pole, and since end of the coil would have south pole, the current direction would be in the clockwise direction. So the face A will have a clockwise direction. Third one, they are asking when the coil is moved away from the north pole. Coil is taken away from the north pole, what happens? The galvanometer deflection will be towards the left. Purely because, as I said, in this case it is going to be the anti-clockwise direction that would take place, and since it is anti-clockwise direction, we would see the deflection towards the left. Then the fourth part, state the observation when both are moved forward or backward or towards the right together. Since both are moving in the same direction at the same speed, we see there will be no deflection in the galvanometer purely because there is no change in magnetic flux. Let's consider what appeared in 2004. Again, as I said, you have these diagram based questions. So they had asked a question to draw a label diagram to show the various components of a step down transformer. Again, as I said, the words are very indicative. We should be very careful while looking at the words. It says it's a step down transformer. That means number of turns across the secondary is going to be less than the number of turns across the primary. The moment I draw a primary, I'm going to draw it as a continuous 3. You know the number 3. Just do not lift the pencil. Keep on twirling your pencil in the shape of 3 to get the primary input. Draw 3-4 parallel lines as indicated in the figure to show the soft iron core material. Across the secondary, we are going to draw a continuous 6, which again is not to be lifting the pencil. So we place the pencil and we keep on tracing 6 together so as to get the corresponding secondary. Remember, number of turns in secondary will be less than the number of turns in primary. Next question that appeared in 2004 was, state the main difference between a step-up and step-down transformer. Basic difference between step-up and step-down transformer was that the output voltage in case of step-up transformer is going to be more than the input voltage, whereas in case of a step-down transformer, the output voltage to be less than that of the primary voltage. In case of a step-down transformer, the secondary voltage is going to be less than the primary voltage. That's how the difference between primary voltage, secondary voltage for a step-up transformer and step-down transformer works. Another major point of difference we can put across is number of turns in case of secondary more than number of turns in primary for a step-up, whereas number of turns of secondary less than the number of turns in primary for a step-down transformer. This was just for 2 marks. Well, another one, explain briefly how a magnet can be demagnetized using an alternating current. Again appeared for 2 marks. Place the magnet in east-west direction. You're placing the magnet in the east-west direction and passing an alternating current through it. The moment you're passing an alternating current through it, it is observed that the magnet gets demagnetized purely because of the magnetic field that has been set up. It is coming under the influence of Earth's magnetic field, and hence we see that the demagnetization effect occurs. Next one appeared in 2005. State the energy change that takes place when a magnet is moved inside the coil having galvanometer at its end. And you are asked to name this phenomena. Obvious answer here is the energy conversion taking place is mechanical rotational kinetic energy into electrical energy. The phenomena taking place here is electromagnetic induction. However, coming down to the next one, again was a diagram based question. A very important diagram to remember, that is a label diagram of a AC generator. When we talk about AC generator, we are just going to talk about the main parts that we care for. That is the magnetic field. We are talking about the carbon brushes. We are talking about the slip rings that are there. And we are talking about the terminals across the external circuit. The moment current is produced, we definitely see that this current is going to be generated so as to run the external circuit. Let's consider this question that again had appeared in 2005. You're asked to state the function of split ring that is used in a DC motor. Well, the function of split ring is to reverse the direction of current. We use the split ring in order to reverse the direction of current in the coil, and it turns through an angle of 180 degrees. So due to the rotation of the coil through 180 degrees, there is a reversal of current, and because of the split ring, we see that the rotation is continued in the same phase of motion, thereby giving a uniform rotation of 360 degrees. This had appeared for just 1 mark in your 2005 paper. Another question that appeared in 2005 for 2 marks was, mention 2 reasons why soft iron core is used within the coil of a moving coil galvanometer. The reason why we use soft iron core material, obvious reasons are to intensify the magnetic field, and second is to keep the plane of coil always parallel to the magnetic field of the permanent magnet. So these are the two uses of using a soft iron core in a moving coil galvanometer. Talking about 2006, with reference to a DC motor, state the principle on which it works. We have to state the principle on which a DC motor works. It had been repeated from 2000 to 2006, again for 2 marks. The principle on which DC motor works can be stated as: when an electric current is passed through a conductor, when an electric current is passed through a conductor placed normally in a magnetic field, a force acts on the conductor. As a result of which the conductor is rotated or begins to move. The direction of force is given by the help of Fleming's left-hand rule. Just to give you a recap of what exactly Fleming's left-hand rule is, we have the fingers of the left hand wherein they are being stretched across so that they are mutually perpendicular to each other. The middle finger shows the direction of magnetic field. The first finger gives you the direction of current. It is the thumb which indicates the direction of force. So if we align our fingers in such a way such that the middle finger points towards the direction of magnetic field, the forefinger acting towards the direction of current, we see that the coil would experience a force that is given by the direction of the thumb. So with reference to this, we see that there is a rotation in the coil. So that is the principle on which the DC motor works. Second one is a repeat question where they are asking you the advantages of electromagnet over permanent magnet. We've already mentioned that, wherein we say that the electromagnet has a higher intensity of magnetic field, the strength of magnetic field can be increased, the polarities can be reversed, and so on and so forth. Second one, what will happen to a compass needle when the compass is placed below a wire and a current is made to pass through it? When the current is made to pass through the wire, we see it sets up its own magnetic field, thereby affecting the deflection in the magnetic needle. So we will see that the magnetic needle would undergo deflection. Another question that appeared in 2006 was, state the energy changes that take place in case of a DC motor. In case of a DC motor, we are supplying it with electrical energy. This electrical energy is responsible to rotate the coil, thereby converting the electrical energy into mechanical, kinetic, rotational energy. So the energy transformation that is taking place in case of a DC motor is electrical energy getting converted into mechanical, kinetic, rotational energy. This is what appeared in 2006. Talking about 2007, what will be the effect of working of an electric bell if instead of an electric bell working on a direct current is made to work on an alternating current? This was asked for 1 mark. If an alternating current is used, then the electromagnet present inside the bell continues to be magnetized and demagnetized continuously, thereby ringing the bell continuously. So this intermittent supply of current causes the electromagnet to get magnetized and demagnetized. As a result, we see that there is going to be a continuous ringing of bell. State two factors on which strength of induced current depends. Again, a repeat question. We say the two factors on which the strength of induced current depends is the number of turns of the coil, and second, the area of cross section of the coil. Greater the number of turns of coil, more is the current induced. Greater the area of cross section of the coil, more is the current induced. This is in accordance to Faraday's law of electromagnetic induction. Another question that appeared in 2007 was, when a solenoid that is carrying current is freely suspended, it comes to rest along a particular direction. Why does this happen? Solenoid is nothing but a circular coil that is wound across a soft iron core. I suspend it freely in air, and of course current is made to pass through. Why is it that this particular solenoid comes to rest after a particular while? We see that when current is made to pass through this, it sets up its own magnetic field. It is coming under the influence of the Earth's magnetic field. Thereby, at a particular position, it will align itself depending on the polarity of the faces of the solenoid, that it would align itself in a particular direction. Let's see what appeared in the latest paper, that is 2008. They asked a point of similarity and a point of difference between an AC generator and a DC motor. So they are simultaneously asking you the similarity as well as difference between an AC generator and a DC motor. Well, the difference between DC motor and AC generator is that DC motor has split rings, S-P-L-I-T. A DC motor has split rings, whereas AC generator has slip rings, S-L-I-P rings. So definitely this is one of the major differences between a DC motor and AC generator. Similarity between the two is that both use a soft iron core to increase the intensity of current. So in order to increase the intensity of current, both these AC generator and DC motor make use of a soft iron core. The next question that appeared in 2008 was, if a soft iron piece is placed inside a current carrying coil, what is the name given to the device? What is the name that is given to such a device? And you are asked to give one use of the same. Well, the device is obvious. It is no less than a solenoid. So when soft iron core is wound across by a particular coil, we say that this particular device is called as a solenoid. It is used in studying the principle of electromagnetic induction. The use of such a solenoid is nothing but to apply to study of principle of electromagnetic induction. Let's consider the next question. Why does a magnetic needle show a deflection of the coil when brought close to a current carrying conductor? As I said, a current carrying conductor sets up its own magnetic field. Whenever we have this particular magnetic field that is set across, we are having another magnetic needle which is placed in the vicinity of it. Definitely it will experience a magnetic force, because of which there will be a deflection in the needle and hence gets affected when brought near a current carrying conductor. If the same wire is wound across a circular path and the current is in anti-clockwise direction, what will be the polarity that the face would exhibit? Well, if the current is flowing in anti-clockwise direction, it indicates the north polarity. How did we get this north polarity? Of course, by Clock-Simpson's rule. As I said, that when the north pole of the magnet enters the coil, current flows in the anti-clockwise direction. Vice versa, current flowing in the anti-clockwise direction, it is the north pole that enters the coil. Another question that was asked was a simple schematic diagram of a step-down transformer labeling its parts. When we are talking of step-down transformer, care must be taken that the number of turns of secondary is less than the number of turns of primary. With this, we conclude the board questions that have come across till 2008. Just talking about a brain map or how we are going to memorize this particular chapter. As I said, it's a theoretical chapter. We started with the concept of electromagnetic induction. What exactly is electromagnetic induction? How does it occur? What are the causes of electromagnetic induction? How is it that when a conductor cuts the magnetic lines of flux, we get the electric current that is generated in it, which is seen by the deflection in the galvanometer. We saw also in this case how magnetic lines of forces have been created when we have a current that is flowing through a conductor. In case of a straight conductor as well as a circular loop. We studied various laws in this case, right from Faraday's law of electromagnetic induction, wherein we said that current flowing through the conductor is directly proportional to number of turns of the conductor, directly proportional to area of cross section of the conductor, directly proportional to rate of change of magnetic flux with respect to time. We modified this law into Lenz's law, which gave you a minus sign in the picture, wherein we had the relation I is equal to minus Na d phi by dt. That is, rate of change of magnetic flux is such that it opposes the very cause that is producing it. This particular part, or the current that is flowing through the conductor, is such that it opposes the very cause that is producing it. This relation of minus Na d phi by dt was the Lenz's law. We had the Clock-Simpson's rule, wherein we had the diagrammatical value wherein we showed N and S polarity showing the current in anti-clockwise direction or the clockwise direction. We had the right hand grip rule also, wherein we say we hold the conductor in our right hand such that the outstretched thumb indicates the direction of current, the curling of fingers give you the magnetic lines of forces, and so on and so forth. So we had a brief recap of all these laws and rules. Then we went on to self-induction, mutual induction, very interesting phenomena, and the device that is based on this, that is a transformer, which was divided into two categories, step-up and step-down transformer. In case of step-up transformer, number of turns across secondary is more than that of primary, whereas in case of step-down transformer, number of turns in secondary is less than number of turns in primary. We have applications of step-down and step-up transformer in day-to-day life, like your adapters that are used in chargers or your heavy duty transformers that are used in case of industries to increase the voltage as compared to the main supplies from the substation. Then we went on to another concept, that was the concept of electric bell, wherein we saw the diagram, we saw how the operation of electric bell worked on the principle of, again, electromagnetic induction. We then went on to a DC motor, wherein we say that DC motor works on the principle wherein electrical energy is supplied to the motor, and then this electrical energy is getting converted into mechanical kinetic rotational energy. Vice versa of this, we went in for an AC generator, wherein mechanical kinetic rotational energy was getting converted into a electrical current, which is exactly what happens in case of a dynamo.